After finding a suitable design of the track structure, a structure that would support the track had to be designed. Our design specification asked for truss structures with the tallest a minimum of 40 centimeters in length. After testing the prototype of the track, it was found that an angle between 4 and 6 was most optimal for the appropriate movement of the ball. A design based of the Warwick truss was chosen, since parallel members easily provide the required height, and alternating diagonals provide the even distribution of forces throughout all members. Considering the given constraints, a realistic truss structure was hard to implement, but we made it so that it resembled an ideal truss. Hence, the first 2D prototypes included vertical and horizontal members of same length to create squares with supporting diagonals, which would then all be glued on the same plane. This 2D face was then used to create a symmetric 3D truss. Both prototypes proved that glue joints were enormously weak and enabled the structure to slant easily, which prompted to create a new design. In the new and final design, it was chosen to connect horizontal and diagonal members on the same plane, while the vertical members became one member throughout the truss. Two of those long vertical members provided a surface onto which those horizontal and diagonal members could be glued to. This design provided much stronger joints in those slanting. Additionally, for extra support and to prevent structural failure, the width of the members was doubled. The design proved to be extremely efficient.
In the ball kinematic section, the only parameter we could analyze with our current knowledge was friction. It is imperative that the ball rolls down the track and doesn't slip, as such it experiences static friction. In the report we have derived an inequality relating static friction to the angle of the slope. Research shows that the coefficient of static friction is 0.4, while experimentally the angle of the slope was found to be 5 degrees. Using these values, the calculations in our report show that the static friction is more than enough for the ball to roll. We used method of joints and sections alongside buckling analysis to analyze structural integrity of the supports, assuming they are ideal trusses. Therefore, the trusses must be made to account for the worst case scenario. Due to this, it can be assumed that any 180-degree turn, because of poor construction, the ball could roll along the slope. The resultant force can be found along with its relative angle by finding the acceleration along the slope. This force can be applied against the top diagonal member of each truss. Calculations show that members are mostly in compression and that the forces developed are mostly well distributed, with no forces reaching the critical load. Some members, however, do not carry any force. In the buckling analysis, the same assumptions stand. Critical loads for each distinct member of each truss pillar were considered, and no member should buckle in the worst case scenario. However, the trusses also carry the weight of the track and must withstand the test of time and multiple trials. Hence, large margin between critical and developed forces in members is vital.
The design specifications meant that the choices for rollercoaster were limited by material and scale. Based off of the point system, the initial thoughts discussed the possibility of the vertical loop-the-loop and varying its angle in order to decrease the energy loss within it. However, after doing the maths behind the required momentum to make it feasible, and realizing it would restrict us to over 100 points, we shifted our focus to the 20 points per 360 degrees. This option had the second greatest points per feature, and if we could bank the track, then speed could easily be maintained, and if the spirals decreased in radius, then the bottom wire for the spiral above could act as the supporting side wire for the spiral below. This idea also decreased the height loss per 360 degrees and allowed us to over triple our points gained than if we went for a helical spiral, while also decreasing the material usage and shaping the track to be an upside down cone. After running with this idea for a day and speculating on the supporting structure, we struggled to conceptualize how to maintain structural integrity with the provided materials. After realizing that the space and energy required for each type of point providing feature was a large factor, I proceeded to look at the 15-point scoring 180-degree turns. Considering that each feature didn't require any loss in height, it meant that we could span the whole surface area of the board space with turns. After mapping it out on base plate and extrapolating it to a declining angle, it allowed us to fit 37 turns on the track, while having none of the track pass under itself. This meant that the trusses could support it without interfering with the route. The next part of the design was to determine the width of the track, as it was desirable to prevent the ball from rolling over the edge of the track, too wide or too narrow, and the wire couldn't support the ball's movement properly. We decided to double the track height and cut into the board to have 4 points of contact holding the ball in place. During the final hours of construction, we had difficulty with the consistency of speed of the ball along the middle declining section, as the ball would not maintain its speed and get stuck. After review, this is likely due to a misalignment when securing the planks and the trusses, as well as a varying width of the track. Due to a limited time schedule before the final run and a healthy amount of points to play with, we decided that the risk of 3 failed attempts due to a lack of speed was too great a risk, and proceeded to end the track at the point where it would most consistently stop, by forming a hole in the track and guiding the ball to the baseboard. The concept of the track worked brilliantly, where the track width was accurately laid.